Greetings, friends, and welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla, and today we'll be talking about an example of an AC circuit. So, there's an awful lot going on for an AC circuit if you include the many things that can be there. So today we're going to talk about how to handle the AC circuit when you have a resistor and an inductor and a capacitor to go along with it all, and discuss all the various ins and outs that you might find. So, with that in mind, let's get started. Let's suppose we have a source of alternating voltage, 120 volts RMS. So that would be similar to what might be coming out of your wall socket, and it's operating at a frequency of 60 hertz. Again, typical wall socket stuff. Let's connect that in series with a resistor of 8.59 ohms, next an inductor of 4 millihenries, and after that a capacitor of 400 microfarads. What we want to find or determine is the inductive reactance, the capacitive reactance, the impedance, the RMS current, the phase angle or phase constant for the circuit, and finally the resonant frequency of the circuit, which isn't necessarily the same as the frequency that the voltage is being driven at. Those are not necessarily the same things. So let's begin. So got our facts listed, our unknowns listed. And if we were to draw a real quick circuit diagram for this without a switch to impede, if you will, what we're talking about, so I'm not drawing in the switch or any other parts of it, your circuit diagram might have this kind of appearance. Here's a circle with a little wave-looking item inside of it. That is our source of alternating voltage. We have our usual inductor, resistor, and capacitor. Okay, so you have seen in the past, either with me in different videos or through, of course, your regular classes, that how capacitance or capacitors and inductance or inductors work a little bit differently with sources of voltage. But those are DC sources. How are they going to play out when we have an AC source? And that's part of what today's discussion is all about. So let's get started. Now, inductive reactance, that's of course due to this fellow here, where is that basically coming from? Well, it's part and parcel of Faraday's law, if you will. If you remember Faraday's law, it has a negative sign in it, which says that as you try or you change the magnetic flux through a coil, for example, you're going to get an EMF generated. But that EMF is in opposition to the direction of the change of the magnetic field, which means that there's kind of a pushback, if you will, all right? So what that means is, well, let's go ahead and find out. It means basically, if you will, that there's something very akin to resistance. Now, it's not officially resistance. It's not official resistance because, at least for an ideal inductor, there's no heat loss due to, say, resistance. There just isn't. We're just simply talking about a natural reaction that the coil has because you're changing the magnetic flux through it. So it acts like a resistance in that there's a pushback to keep current from flowing, but it's not resistance because, at least in ideal cases, there's actually no loss of energy. So that means instead of calling it resistance, we have a different name for it. It's called reactance. The coil reacts to the presence of a changing current and a changing voltage. That particular symbol for that is the Greek letter chi. So that looks like an X because it is an X. Or in English, we sometimes have an X with a C or hard K sound, and that's maybe how to best remember it. Now, because there's more than one possible reactance, we do need to give it a subscript. That's L, so inductive reactance is what we're talking about there. So this will still have the units of ohms because, again, it's a device that, or a situation where you're trying to keep or try to impede, if you will, the flow of current through it. But it's not resistance. So it's a little bit different. The formula for inductive reactance is omega L, like that. Okay, well, that begs the question, where is omega? Well, let's do a little bit of that first. So omega is our angular frequency. And we've seen that before in other places. It's still the same formula as you've encountered in the past. Say if you're dealing with vibrating springs or with waves and mechanics, 2 pi multiplied by straight up frequency. So at least in the United States, the typical frequency for a wall circuit is 60 hertz. I say that just to mention that it's not a necessary, say, thing of nature. There's no rhyme or reason except 60 is a common number for time, and that's how the United States decided to work it. But there are other places where the frequency is 50 hertz instead. So you don't have to have it as 60. But in this particular country that I'm in, that's very common. So 2 pi multiplied by 60 hertz. And again, save a little bit of time. I've done the math ahead of time. 377 radians per second. So that will come in handy, all right? Now, you could either use it straight up like this, or if you prefer to write it out more fully, you could do that. And that's perfectly legit too. That's perfectly fine. Okay. So let's go ahead and take this a little step further then. Now, what is this inductive reactance, which we were talking about before? 377 radians per second. And the inductance was 4 millihenries, or 4 times 10 to the negative third henries, like that. And when we make that calculation, we get 1.51 ohms. So a small amount of resistance, but it's also not zero. Okay. How about capacitive reactance then? Capacitive reactance. So capacitive reactance has a slightly different looking formula to it. Capacitive reactance, and again, subscript C for capacitive reactance, is 1 divided by omega C, like this. So it looks an awful lot like that formula, except flipped. All right. Also notice how the units are going to play out for us. If you look here, ohms are really equal to henries per second. Okay, remember that radians disappear when you make a calculation like that. Whereas this is going to have a little bit of a different take, if you will, on the units. But we still will end up with ohms. And there's a similar sort of thought process here very quickly. A capacitor also has something akin to a resistance, right? As you pile more and more charge upon a capacitor and upon the plates of a parallel plate capacitor, for example, what's happening is that those charges are giving you a reaction or resistance to putting more charges on it. And so we have, again, something that's akin to resistance. But again, it's not resistance in that there's no energy lost. So there's no thermal energy that we generate that way, at least in ideal circumstances. And so it's not a true resistance. And so again, we call it reactance. The capacitor is reacting to the presence of a current. All right, calculate. So 377 radians per second again. And now it's 400 microfarads, or 4 multiplied by 10 to the minus 4th farads, like that. And when this calculation happens, again, as always, check my math, 6.63 ohms that way. Okay, so capacitive and inductive reactances. Okay, I've chosen some numbers that will work out nice and neat for us, of course. That's kind of the point of some of these things. But that gives us a little bit of a flavor of how you're going to calculate it. Also note the units. This is per, so seconds is actually on top if you do this, because it's 1 divided by 1 over seconds. So seconds per farad also yields ohms as units, strangely enough. All right, what do we do then to get the next step? So there's something called impedance. And impedance is really just the overall, say, idea of resistance-like things all put together. Right? So resistance, capacitive reactance, inductive reactance, all jumbled together. Now, this is a video in which we're not doing a lot of discussion on the theory of this. I leave that to your instructors or to your textbooks. But I will cite the example or the conclusion, and that is, say, impedance, which we use a capital Z in physics to represent, is equal to R squared plus the subtraction chi L minus chi C, quantities squared, like that. By the way, a way to remember this, and again, something that your instructors have hopefully talked about, this looks an awful lot like Pythagorean theorem, doesn't it? Like an A squared equals B squared type C squared sort of thing. Because it is. It is. There's a kind of a wild way to get there, but the formula looks like a Pythagorean theorem kind of calculation, because it is in the long run. So Z then is the square root of all this, right? So R squared plus chi L minus chi C, quantity squared, like that. So R was 8.59 ohms squared, we have a 1.51 minus a 6.63 ohms here. Like that, okay? And just to write this up so everybody can see my final result, if the numbers look kind of funky here, I did choose them on purpose to make it work out the way I wanted it to work. Lo and behold, 10 ohms is where we land. So yes, I made that artificially work out to be that way, but it doesn't matter. If you think about it, almost all these examples are artificial to some extent. I wanted to have a simple number going forward. So anyway, notice, by the way, that chi L minus chi C is 1.51 minus 6.63. That's a negative number in here. That's perfectly okay because that negative number gets squared, and as you all know, when you square a number, whether it's positive or negative, you come up with a positive result, right? So the difference here is all that matters, really. That will have a meaning for us in a different calculation, but this particular calculation, it's fine. So we don't have to worry about that. All right, we've got a few other things to talk about, including the current. So let's get there. All right, so next step is the RMS current. Now, how do we calculate that? So if I have RMS voltage and an RMS current, what do I do to get the next step? Now, in the past, if you had, say, a resistor circuit, it was simply V equals IR, right? I've mentioned in a previous video, and I'll mention again here, Ohm's law is one of the most versatile types of formulas, general formulas we have in all of physics, because you can use variations of Ohm's law for all sorts of things, including here. Now, if you have a full-blown AC circuit like we've got here with resistors and inductors and capacitors, it's not the resistance that goes here now, nor is it, for example, just the inductive reactance or the capacitive reactance. It's this combination, which we called impedance. And so here's why we would go ahead and solve for impedance earlier. If we want to find out or predict what the current should be, specifically here the RMS current, we need the RMS voltage and the impedance. So that's why we're kind of taking this long route, if you will, to get there. All right, but notice this is really Ohm's law, isn't it? V equals IR, or what used to be V equals IR, right? So it's a version of it, but it's a version specifically built for these AC circuits. All right, we're solving for RMS current. So that is RMS voltage divided by impedance now. The RMS voltage was 120 volts. The impedance was 10 ohms. Yes, I did that on purpose to make this easy. 120 divided by 10 is 12. So 12 amps, and that is RMS current specifically now, isn't it? So interesting that that comes out that way, but that's how this works. So if I want to find or relate RMS current to RMS voltage, I need to go through these steps. Now, if you look at this formula briefly here, let's get this one back for the impedance, just to comment quickly for this formula. Let's suppose you have no capacitor and no inductor. That means there's no parts here, and look what happens. Z squared equals R squared, or Z equals R. You're back to your normal or your original version of Ohm's law, right? V equals IR. So, and you can play with this, of course, if there's no resistor, but there are these two devices, or just one of these, you can see how that might also sort of change what you look at. But without a capacitor, without an inductor, these go away, and you're back to that original statement of Ohm's law that we started you with some time ago. All right, so back to what we need to solve for. Let's go ahead and take a look at the phase. Okay, so that was part D for the RMS current. Part E is this phase angle. Now, what is this phase angle business all about anyway? The phase angle is simply this statement that dependent upon the specific numbers that you get for, say, capacitance and inductance and the currents that go into them and a resistance, the voltage will go up and down in according to a sort of a specific pattern. How that pattern plays out for the entire circuit is related to the phase angle. Okay, so electronics people, electricians, will want to know that. What is that formula? Well, it's chi L minus chi C divided by R. Now again, if this looks familiar, it does, right? tangent of an angle is the opposite side divided by the adjacent side, right? And it's, again, got that kind of flavor to it. Again, I'm not going to go through exactly how that's derived. I leave that for other places. That's not our intent here. But I do want to remind you that's sort of where it's coming from. And it might help you remember how this works. So, go back to our numbers. 1.51 ohms minus a 6.63 ohms. And then all of that divided by the 8.59 ohms we had from our resistor. And just to write it down, this number was negative 0.596. Now, that's not the last step, right? Because if we want to solve this, we really want the angle, not the tangent of it. So the phase angle by itself is the inverse tangent of this, right? Notice, by the way, there's no units on this number. Ohms cancel, as they should. And when we solve for that, we get this as our angle. Okay, so that's the phase angle. And again, that's a quality of the circuit. That's basically telling you how the voltage and current are, say, rising and falling together. Or, in this case, not together for the entire circuit. Okay. Last thing to talk about is something called the resonant frequency. Now, to give you a flavor of this very quickly, and to take a non-electronics example, suppose you're asked to push a child on a swing. So you get maybe a sibling or a cousin or somebody you're babysitting, and you go to the park and you're pushing this young child on a swing, and the child asks you to push them higher and higher. How would you do that? Well, you don't just push at any point during their swing. When they're going back and forth like this, and you know this from experience, right? The best place to push them is when they hit right at the peak of their swing, and then give them a push. Why? Because they have the maximum potential energy as possible at that point, maximum gravitational potential. And if you push there, you add in kinetic energy. And so they'll go higher and higher when you do that, okay? Obviously to a certain point, but yes, that's how that works. Well, we have a similar sort of thing here. If we set the circuit's frequency to, or the source of voltage's frequency to the resonant frequency, we can maximize the input of the circuit. We get the most bang for the buck, so to speak. So again, something we might want to know. So just to remind ourselves earlier, the actual frequency that this circuit was using is this. So that's what the source of voltage is driving. And that's what's going to be used in the circuit. But we could avoid or have a better, say, outcome for the circuit if we go to a resonant frequency. Again, I'm not going to solve for that. I'll simply give you the result. But it's sort of an interesting one in that it looks like this. So the resonant angular frequency, written it as angular frequency terms, is 1 over the square root of L and C together. All right, so let's put in our numbers there. So L, again, was 4 millihenries, or 4 times 10 to the minus third henries, right? The capacitance was 400 microfarads, or 4 times 10 to the minus fourth farads, like that. So when you're calculating, by the way, it's probably simplest to take this number, multiply that number, get your result, take the square root, and then invert it. So that's the process I would go through if I was doing that calculation. And when I did that particular calculation, this is the result we come up with. Which is to say, this circuit would do better, so to speak, if you will, or give you a less loss of energy or power in the circuit if the broadcasting or the source of voltage was alternating at that particular angular frequency, instead of, say, the 60 hertz or 377 radians per second that is. So anyway, this is then what we have for all of our answers. Notice there's a lot to talk about, right? There's a lot of input we needed to solve for it, and there's a lot of output. But if you do this in sort of sequence, and if you look at each individual calculation, none of them are all that difficult. It's just that there's a lot of it, unfortunately. That's just one of the deals we have to do. Something you have to deal with sometimes, right? You just have a lot of things to know. But the individual calculations are not too terribly difficult. They aren't really that bad. Okay. So, all right. So, technical support for our programs is from Sydney Galtrau and Sophia Turner. Funding for this comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Sorolla, broadcasting from Hattiesburg, Mississippi, thanking everybody for your attention today, and clear skies.